Hello, welcome back to Engineering 201 Electrical Fundamentals, and I wanted to go on and talk about some other analysis techniques, probably not as universally useful as node or mesh analysis. Those are going to be our big tools in the toolbox, but tools that are useful and also show us other ways of thinking about circuits. And the first one I'd like to look at is superposition. We're going to use this for only independent sources. If you're really clever, you could actually use it on dependent sources. Those are the diamonds, but we're going to stick with just independent sources. Those are the circles. And the technique, what you do is you essentially short out a voltage source. And solve. And if there's 3 voltage sources, you would short out one voltage source and solve it, and then you'd short out another voltage source and solve it, and then you'd short out a third voltage source and solve it. And if it has a current source, you open and so if it has a voltage source, you short it out and solve the problem. If it has a current source, you open it, the current source, and solve the problem. So let's say we have a circuit that has one voltage source and one current source. We would short out the voltage source and solve it. Then we'd put the voltage source back in, open the current source and solve it, and then essentially superimpose or lay our solutions one on top of the other and add together what we got. That may be a bit confusing, so I think probably the best way to proceed is just an example, and I think that should help some. So let's say that we have a example problem like this. So it's got a couple of sources, so we're probably not going to do it with circuit simplification. You could use node or mesh analysis, but let's try superposition on this. So it's got 2 sources, so I'm effectively going to have to solve the circuit twice. I'm looking for I3, so I'm looking for that current right there. So I'm going to go ahead and open the current source. So if I open the current source, let's see what this looks like. We're going to have the voltage source remaining. And then when this is open, we'd have something like that. Now this is the unknown that we're looking for, kind of. Maybe we should call this I3 prime, because it's not really I3, but we're going to use it to get I3. And if I'm going to write these primes and whatnot, I'd probably better get a little better pen for this. So I've opened, I've taken this out, effectively removed that, the current source. I've opened the current source. This is still 6 ohms and 3 ohms and 2 ohms and then 4 ohms. So now what I need to do is I need to figure out what I3 prime is. So I could, let's say, come back to a circuit that looked like this. And what would we have if I come up with the total equivalent resistance? So I'm looking at 2 and 4 in series, that's 6. So I have put 2 plus 4. Then I'm going to put that in parallel with 3, so that gives me 2 ohms, right? So now I have 2 plus 6, which gives me 8 ohms. So I'd have 120 volts divided by, that is this current here, would be 120 volts divided by 8 ohms, which gives me 15 amps, right? So I now know that if this is 15 amps, that this has to be 15 amps. And I could look at dividing that. So I could say then that So I3 prime is going to be equal to, this 15 is going to be divided. Some of it's going to go here and some of it's going to go there. So I'll take 15, I multiply by the other resistance, which is going to be 3, and I divide by the sum total. Remember that I have this 2 and this 4, which are in series, which gives me 6. So I'll have 3 plus 6, which gives me what? 9. So I'll come up with 5 amps. Okay, now that's not I3, that's I3 prime. So I'll just set that aside and look at this voltage source. So what I'm going to do with this voltage source is I'm going to short the voltage source. Remember, we are shorting voltage sources. We've opened the current sources. We've done that one. Let's go back and short the voltage source. So what that looks like is this then. You got 12 amps, 4 ohms, 2 ohms, 3 ohms, 6 ohms. This is page 2, and we're going to say that this current here is I3 double prime. Okay, it's not I3, it's not I3 prime. It's different, so I3 double prime. So let's see if we can come up with that. What's that going to look like? If I want to reduce that, essentially, I could reduce that to a problem that looked like this. So we've got 12 amps. This would be 4. And then I have 6 and 3. So 6 in parallel with 3 gives me 2 ohms. And then 2 ohms plus 2 ohms gives me 4 ohms. So I'd have 4 ohms there. So if I have 12 amps coming up here, and as a choice of going some through 4 and some through 4, it would be an even split, wouldn't it? So I should be able to say then that this current here, which would be the same as the current there, which is really the same as that current there, I could say that I3 double prime is equal to what? 6 amps? Okay, that essentially comes from 12 amps times the other resistor, 4 ohms, divided by 4 ohms plus 4 ohms would be an even split, wouldn't it? We'd have 6 amps. So we've got 6 amps, we got 5 amps, so this is how we put them all together. And this is what superposition does. We take this essentially and lie it on top of that, and we could say then that I3 is equal to I3 prime plus I3 double prime. So what do we have for I3 prime? We had 5 amps plus I3 double prime is 6 amps. Let me double check that. Yep. And this turns out to be 11 amps. Okay. So, you know, this isn't probably as universal. I mean, you can, a lot of problems, if it has a lot of sources, you'd have to do this over and over again. If it has dependent sources, you probably want to stay away from it. But this is a useful tool and also an important concept to illustrate. You just open the current sources and solve it, then you short the voltage sources and solve it. And let me be clear, if you have to do this for as many sources. So if you have 2 voltage sources and 1 current source, you're going to be doing this 3 times. We had 2 sources. We essentially went through this process twice. Well, let's check this answer. Maybe we will spend a moment and give it a whirl with one of our other techniques. Let's see, I jotted some notes down here. Could we do this with, what about node analysis? Node analysis might be pretty good on this, right? So, try node. So I could say, let's see, if I put this as I3, why don't I call this I2? And we could say that this is I1, and we probably need to call this I4. I'll call this up here V1 at this node, and I'll call this V2. Take this as our reference ground. So if I try node analysis, I've got two equations. I could say that I have I1 plus I2 plus I3 is equal to 0, Kirchhoff's law. And then I3 is equal to I4 plus 12. I3 is equal to I4 plus 12. Yes. Okay, so now I need to define I1, so I have to look at the voltage opposite that. So that would be V1 minus 120 divided by 6 plus I2. That's an easy one. That's just going to be V1 divided by 3 plus I3. And we have to go opposite that. So V1 minus V2 divided by 2 is equal to 0. And over here, again, I've got I3, so V1 minus V2 over 2 is equal to, what's I4? That's simply that, V2 divided by 4 plus 12. So I'll multiply this thing by 6 and come up with V1 minus 120 plus 2V1 plus 3V1 minus 3V2 is equal to 0. So how many V1s do I get? 5 of them. 6V1 minus 3V2 is equal to 120. So that's a nice equation. And multiplying this by 4, I get, what am I going to have? 2V1 minus 2V2 is equal to V2 plus 48. So how many V2s do I have? I guess V1s first. So 2V1 minus 3V2, sorry, yeah, minus 3V2 is equal to 48. Double check my notes, make sure I got those equations right. Yes, I think we're good. So two equations, two unknowns, we could solve these. What am I looking for? I'm really looking for this current here, aren't I? So I'm going to essentially need this current I3 is a function of V1 and V2, so I really need to solve for both of those. Sometimes if you just need to find one or the other of them, you want to affect your substitution that way so you can get to it faster, but we got to do both of them. So we could put these together and say that I have what, minus 6 V1 plus 3 V2 is equal to minus 120, multiplying that by minus 1. Then when I look at this one, I've got 2V1 minus 3V2 is equal to 48. This would be negative, yes. So when you add that together, we have, what, minus 4V1, V2's cancel out, is equal to minus 72. Negatives cancel, and you get V1 is equal to, what, 18 volts. So if V1 is equal to 18 volts, we could take and substitute that in now. So if you substitute that into there, you're going to get 2 times 18 minus 3V2 is equal to 48. Close to the end there. So V2 is equal to minus 4 volts. Okay, V1 is equal to 18 volts, V2 is equal to minus 4 volts. So what do I do with all this? Well, I come back and get I3. Therefore, I3 is going to be equal to V1 minus V2 divided by 2, which I have V1, which is 18, minus V2, which is a minus 4, divided by 2, which is what, 22, because negatives cancel, so I have 22 over 2, which is 11 amps. Just what we got over here, right? Okay. So you could say, well, this is easier, this is not easier. That's not necessarily why we talk about this, just to give you more tools. And again, oftentimes I come back and practice node or mesh analysis, because those are really our number one fallback positions, just so that we're really good at that. So the motivation here was to practice superposition, and then I wanted to also practice node analysis and double check my answer, and indeed it works out. Well, let's continue on, and the next thing I want to do, and maybe I should start with a clean sheet here. Let's see, that was 2, this should be 3, this will be 4. The next thing I want to do is I want to look at source transformation. Okay. So with source transformation, what I can do is, if I have a voltage source that is in series with a resistor, I can switch that to a current source that is in parallel with the same resistor. And if I look at these terminals, let's say A and B, and this terminal A and B, from the terminals we will not notice any difference. Now the question comes up is, what is this current source? Well, that would be equal to V divided by R, by Ohm's law. And likewise, this voltage here, V, would be equal to I times R. So we can not only convert a voltage source that's in series with a resistor to a current source in parallel with a resistor, we can go back and take a current source that's in parallel with a resistor and convert it to a voltage source that's in series with a resistor. So this is called source transformation. We'll actually see this more and more when we start talking about Norton and Thevenin models. This is in fact a Thevenin model, and this is a Norton model, so you just do a source transformation from one to the other. Again, most of the time with this, when we get Norton or Thevenin models, we'll talk about how we can do it on all circuits, but again, for source transformation, to keep things simple, let's stick with, for now, dependent, or excuse me, not dependent, independent. So we'll stick with independent sources for now. Okay, so that's the gist of it. Again, let's apply it to a problem. So how could we do this? Well, we notice on this problem that I have 60 volts in series with a resistor, so I could convert that to a current source that's in parallel with a resistor. So let me do that. Let me say that I have then a current source. So let's see, I is going to be V divided by R, which would be what? 60 divided by 6. So I have 10 amps, right? 10 amps. And the direction, your current will go in the way the current goes through that source. So we'll have something like that. Okay. Now this is the same 6 ohms. Then over here we could we've got what? Very, very similar thing. So I could take my resistor that's in series with a voltage source and make it a current source that's in parallel with a resistance. So this will be 3 ohms. And now you notice this is negative to positive, so that would mean this would go down. I mean, we could turn it around and have it go up and then have a negative value here, but I think I'll make the arrow go down, the current source go down, and this is going to be what? 15 volts divided by 3 ohms, which gives me 5 amps. So I'll have 5 amps here, or 5 amps negative if you want to put that arrow going up. Now, all I have to do is put this 3 ohms in the middle, right? So I just hook these together and put this 3 ohms right back in the middle. Now what I can do is I'm looking for this current here. That's what I'm looking for. That current right there, and there it's still there, isn't it? So what I'd like to do is try and simplify this, and if I look at this, if I look at the current flowing from this node to this node, essentially putting these current sources on top of each other, I could really represent this like this. I've got 10 going up and 5 going down. I would have a net 5 amps going up, wouldn't I? And then what about this 3 ohm here? And that 6 ohm there. Those are really in parallel, aren't they? So I have 6 ohms in parallel with 3 ohms. Product over sum gives me 2 ohms. So I'll have 2 ohms there. And then I still have our friend there, the 3 ohms, with our unknown current, I naught. Well, current's got pretty easy now. This goes back to the problems we had at the very beginning of the term. We could use current division on this. I could say that that's 5 times the other resistor, 2 ohms, divided by 2 plus 3 ohms, which gives me 2 amps. Okay. So source transformation can be very handy. Sometimes you'll then make some changes and then you might transform it back. That's always a possibility. Well, let's see. We've got all kinds of methodology now, don't we? Let's try superposition on this same problem. So once again, the exact same problem. This was on page 5. This is a source transformation. Okay, and I think that was a quick little tool on that. Let's try superposition. Okay, what's superposition look like on this? What do we do with our voltage sources? Well, we short them out, don't we? So I'm going to look at 2 problems. I'm going to look at one problem where I have the 60 volts remaining. And when I short out that 15, I'll get something like that, right? So I've got 6 ohms and 3 ohms, 3 ohms. This is our short, and this is I naught prime. And then I'm also going to have to look at a situation where I've shorted out the 60. Be careful of the polarity here, minus positive. So that remains the 15 volts, 3 ohms, 3 ohms, 6 ohms. This is shorted out, and this is not I naught, it's not I naught prime, I naught double prime. See, can I do that? Well, let's see, I'll come back over here. Could we figure this out? Well, I could say that this is, if I were to reduce this to a single resistor, what would we have? 3 in parallel with 3 gives me 1.5, right? So 1.5 and 3 in parallel with 3 gives me 1.5 plus 6, so I have 7.5 ohms. So that current there, I, is going to be equal to 60 divided by 7.5, right? And then I just have to divide that. That's going to come up to this point here, and it's going to divide evenly because these are the same resistors. So I could say I naught prime is equal to 60 over 7.5, and I just divide that evenly. So I'll multiply that by 2. Let me check my numbers on that. Yeah, 4. Good. Okay. So that's I naught prime. Let's try this one. I naught double prime. What am I going to have there? Well, if I were to reduce this, I've got 6 that's in parallel with 3, so that's 2. So 6 in parallel with 3 is 2. So I essentially have then 1 resistor. That's 6 in parallel with 3 is 2, and 3, that gives me 5. So 2 plus 3 gives me 5 ohms. Now I have to be careful with the polarity here. I'm going to get a current, this I, which is going to be equal to, what, 15 volts divided by 5 ohms, which is, what, 3 amps? Now that's going that way, isn't it? Okay. If you chose to say that the current was going this way, what would it be? Well, that one would be minus 3 amps, wouldn't it? Okay. Well, so let's see. How can I split this? I'm essentially going to say that, so I naught double prime is equal to, maybe I'd better say minus 3 amps. Because if this one's going like that, I need to find the current that's going there, don't I? I need to find that minus in relation to that minus 3. What's coming around here and going like this, that's going to be minus. We found this was positive 3. So I have minus, and then what's the split on this thing? Looking for the current going through here, so I'm going to use that resistance. So that's going to be 6 ohms divided by what? 6 plus 3 ohms. Which is what, 9, a third of 6 gives me what, 2 amps minus 2 amps. So I've got to have that negative in there. So I can say then, therefore, I naught is equal to I naught prime plus I naught double prime, which is equal to 4 plus a minus 2, which gives me 2 amps. I think that's what we got with source transformation, 2 amps. Yeah. I think our source transformation, if you ask me, it was easier, but we don't want to just say, well, I'm always going to use source transformation, because certain problems will definitely lend themselves to one method or another. Well, what are some other methods that we know? We have node and mesh analysis, right? And I'd encourage you, as you are working through your problems, really exhaust all the techniques. Make sure that you really understand the concepts here. So let's try this problem. We could try it with, we've done what? Source transformation, superposition. Maybe we'll try node. Should be pretty easy with node, right? Take this as our reference node, put our voltage V up here. Take the current I1, take the current I2. So we've got that I1 plus I naught plus I2 is equal to 0. I1 leaving, I naught leaving, I2. Yep. So then I need to write I1 in terms of the voltage. So I'm going to have to go opposite that, which is minus 60 plus V1, or V minus 60, divided by 6. Plus I naught, just have to find that voltage there, V over 3, plus I2, again, I've got to go opposite that, so I'm going to go from there to there, which is now positive 15, so I can say V plus 15 over 3. Remember, over here I was going this way, because I needed to be opposite the current, so I had to go there, which is a minus 60, and then back up there, which is V. So minus 60 plus V here, 15 plus V equals 0. So when I multiply that thing by 6, I have what? Minus, I'd have V minus 60 plus 2V plus 2V plus 30 is equal to 0. Alright, so how many V's do I have? A V and a V, I got 5V. Is equal to minus 60 goes over as a positive 60, negative 30 goes over, positive 30 goes as a negative 30, so I have then positive 30, 60 minus 30. So V is equal to 6 volts. Now, I was looking for I naught. Well, what's I naught? I naught is that right there. So I naught is equal to V divided by what? 3 ohms. So I have 6 volts over 3 ohms, which is 2 amps. Good. So that's node analysis. And node analysis is a struggle to learn the directions of the voltages versus the currents and things like that. But oftentimes it results in less equations, and you can get to things pretty fast. So source transformation is good. Superposition is good. A lot of times my first reaction is node analysis. Although on this one, you could do mesh analysis if you want to. So let's finish up with that. So mesh. Same problem. I'm just going to say that this is IA, and let me say that this is IB. Okay. So I could write a couple equations. If I start here and go around, I'm going to have minus 60 plus 6IA plus 3IA minus IB. Gets me back to my starting point and equal to 0. So how many IAs do I have? I have 9 IA. So I have 9 IAs. 9 IAs, and then minus 3 IBs is equal to 60. So that's a nice equation, but 2 unknowns, so I need another equation. So let me write the equation over here. I could say maybe I'll start here. I can start anywhere, and I just have to work my way around. As I go through this one, that's a gain. So I'll say minus 15 plus around here, then I'm going to drop through this, plus 3 times IB minus IA plus 3 times IB, going up and around through that. Gets me back to my starting point there. I can say that's equal to 0. So what do I have? Minus 3IA plus 6IB is equal to 15. So I need to solve this equation simultaneously with that equation. And let's see, we're looking for I naught, so I naught is really going to be equal to IA minus IB. So again, we need to find both those, so there's not really any preferred method in our substitution. Well, what would be a good way to go with that? I could multiply this by 2, so I have 18 IA minus 6 IB is equal to 120, and then I've got minus 3 IA plus 6 IB is equal to 15. So when I add those together, I get 15 IA, IB's cancel out, is equal to 135, so IA is equal to 135. These are volts, so that makes sense. We'd have volts divided by, this is actually ohms, isn't it? If you look, that's volts, that's ohms. So 15 ohms, which gives me what? 9 amps. Volts over ohms is amps. If we're dealing with kilo-ohms, we'd have to be more careful. We'd come up with milliamps probably, or we could convert. Well, we got IA, so I could just run back and pop that into there if we wanted to. So I'd have 9 times 9 minus 3 IB is equal to 60. So we've got minus 3 IB is equal to 60 minus 81. IB turns out to be equal to what? Minus 21, 3. The negatives cancel, so essentially we have 21 over 3. 7 amps. So we've got IA and IB, and from that we can say that up here I naught is really what? It's equal to, it's going in the direction of IA, so it's IA, but IB is opposing it. IB is coming around like that, so I'd have to subtract off IB. So we have IA, which is 9, minus IB, which is 7, gives me 2 amps. Okay? So as you go through these problems, sit back and think, could I solve it a different way? And try it. And you build some confidence in the answer and also get a lot of practice in the different techniques. But we've got our 2 big players. We've got node analysis, we've got mesh analysis, but hopefully today we added some other tools that sometimes come in very handy. Sometimes you can even use a combination of these tools, that is source transformation and superposition. Well, we'll talk more about source transformation in the future because that's going to lead us into our work in Thevenin and in Norton. The only difference between a Norton and a Thevenin model is a source transformation. So that's where we'll go when we get together next time. Take care till then, and thank you for listening.